So passive transport, the word passive transport, is two big broad categories of transport. And if you look at the top, it says passive transport.
This was on the test.
There was one on the quiz. There's an extra credit question about passive transport, correct? Passive transport is a process that does not require any extra energy. Everything that moves requires energy. We know that. But you don't have to add any extra energy with passive transport. So let's talk about what diffusion is. Who knows what diffusion is? Diffusion.
Is diffuse a single word? Because I might know what it means. I know if diffuse means separate. So like it's spreading out.
Good. Separate it. I love it. Excellent.
Okay. Like being a scientist. Yes, I am. I've been a scientist.
Okay, so if we have water and there's some solutes in the water, let's look at sodium ions in the water. We did this, yes?
Yeah.
Okay, I thought we did. I wasn't sure.
No, we ain't finished though.
Yes, we did.
We
Okay.
put it, all right. So we have if we have high, it goes to low. Correct? Everybody okay with that? All right. So you did. I thought we did.
The faster it moves.
Yeah. Okay. Good. So we don't need to do that again.
You said equilibrium.
Let me go back there.
Yeah. That's right. Average kinetic energy is when is temperature, and when you're at dynamic equilibrium, that's when both sides are equal, but they're moving in opposite directions. Everybody okay with that?
Yeah.
Okay. Is that where we left off? Is that it? Okay. So that's dynamic equilibrium. That means for every one molecule goes in one direction, you have a molecule that goes in the opposite direction. So you have no net change, right? But there's always movement. So now let's take a look at three different possibilities. Eventually, yeah, you have things balancing out is correct. It's called equilibrium. And I misspelled it in the thing, so let's make sure we spell it correctly. Equilibrium. And it's dynamic.
Excuse me.
Yes, I would draw this. Dynamic equilibrium. So if we had three beakers and we had three cells and we use a simple in-out model of a cell, right?
Yeah.
So we can take a look at one. We can have one. What are the different possibilities for concentration, right? So the first possibility for concentration is that you could have, let's say, 10% X meaning anything, sodium, chloride, sugar, whatever, dissolved in there, right? And outside you can have 90% X. Now the percentages, the bottom line is there's more X outside than there is inside, right? That's the point. What's another possibility? That's one possibility. We have more outside than inside, right? X is just some variable, whatever it is. What's another possibility?
More inside than outside.
Okay, but can I do something else first just because it's in the middle? Can I? They could equal, yeah, thanks. So you can have, maybe it's 10% inside X and 10% outside X. All right, so they could be equal. Or let's go to your idea now. It could be opposite, right? It could have higher inside, 90X inside, and 10% X outside. Right, so those are our three possibilities. Everybody agree with that? You have more outside than inside here. 90, 10, you have equal, 10, 10, or you can have 90 inside, 10 outside, so it's higher inside. Everybody okay with that?
Okay, wait. Go ahead. That's 10 inside. Can you zoom in a little bit?
Yeah, I'm going to assume it, but does everybody understand that so far? Okay, so let's look at the first situation. 90% outside, 10% inside. So what is going to happen here? If assuming, now we got to assume here. We have to assume something.
Wait, what are these supposed to be?
This is solutes. So let's assume for a moment that X is soluble. That the membrane will let it through. Let's assume the membrane will allow it through.
Alright.
What's going to happen? Well, it's dissolved. You have 90% outside, 10% inside. What's going to happen? Things move from what?
It's gonna move
It's going to move in what direction?
to
In or out? Into the cell, out.
Out.
In.
Why? Make a
out.
choice. Why?
It's out. So
Wait,
because
so go ahead. What are you saying? Go ahead.
out.
90% is more, it's gonna overpower the 10%.
Well, let's not use the word overpower. It worries me.
It will
But
move out with the
well, if you got 90% out here, there's more stuff out here, right? And so it's going to move in more than it's moving out. So some's going to move out, but there's more is going to go in, correct? So what's the net direction? Into the cell. So the solute would go in. Agreed?
Because it's over.
Because there's more. Now let's not say overpowered. Let's say it's more outside than there is inside. So now let's hear you got equal amounts. So yes, it is dynamic, so you're going to get some going out, but then what's going to happen? Some going in. So they equal out, so they're balancing. There's not going to be any change.
No change.
And here, 90% inside, 10% outside, what's going to happen is that the 90% inside is going to go out. Correct? All right. So that's if it's soluble to the membrane. But if it's a big molecule or if it's charged, it won't go through the membrane easily. So if the solute can't move through the membrane, then what do you think is going to happen? Okay, that's a possibility. That's not what happens, but it is a possibility. You're right. So let's assume that it can't go through the membrane. What's going to happen if X can't go through?
It's going to stay there?
Well, what ends up happening is water will move. If the solute can't move, cannot move across the membrane, then water will.
Because something always got to move.
Yeah, it's always moving. And if you have a bunch of stuff in there, you're crowded and water's a molecule too. It's moving, it's crowded. It's going to move to where it's less crowded. Right? That's just the way it is. All right, so if the solute can't move, then water will. So now let's go ahead and take a look at this example again. So here you have this cell. It's sitting there. So you got 90% inside, and you got 10% outside. Now, can I say something? Okay, let's look at something here. I'm going to go ahead and zoom in. Let's look at this pie. Let's make a pie over here, a pie chart. Right? A horrible pie chart. But
Really don't. Right.
as if you could do better. But anyways. So that's 90% solute and about 10% water. Right?
Actually, that's a good estimate.
It's close, I think, but who knows? So 10% water, right? Why? How do I know it's 10% water? Because it's either what? It's either water or it's solute. So if I'm saying to you that 90% of this is X, right? Then 10% has to be water, correct?
Yeah.
Then out here, I'm going to draw another pie chart. That's horrible.
Right, though.
And it's not that much better, but it's a little better. So that's not even 10%. So here you have 10% solute. Now this is 10% solute. Right? And it's what? It's 90% water out here. So this is 90% water. So things always move from high to low. Water is going to move. So water is going to move from its high to its low. So if this can't move, in what direction is water going to move?
Out. Or in. No.
In.
Wait.
Whatever.
From its high, whatever answer's right.
Out.
From its high to its low.
It's gonna move out.
Where, okay, you're saying out, but remember, this is 90% X inside, so it's only 10% water. Out here, it's 10% X, so it's 90% water. So out here is 90% water, here's 10% water.
Oh, in.
So it's gonna go in.
Well, I'm not letting it go out.
So water moves in the opposite direction of the concentration of solute, right? The reason that water does that is because wherever the solute's the highest, the water is the lowest. Wherever the solute's the highest, the water's the lowest. Wherever the solute's the lowest, the water's the highest. Does that make sense?
Yeah.
So they're going to work opposite each other.
Whoever is more water, that's when the solute.
It's going to go, well, yes, that's correct. So, but the key is this. Water will move, will diffuse, right? Will diffuse, just like solutes will diffuse. Water will diffuse in the opposite direction that the solute would diffuse. If the solute can move. So if the solute can move, it would move out. You're all correct. Everyone said that, right? It would go from 90 to 10 because this is high, this is low. If it could move, but it can't. So now water has to move. In what direction is water going to move? Opposite. It's going to go from its high, which is out here, because even though it's 10% solute, it's 90% water. And here's 90% solute, but it's only 10% water. So it's going to go from, so the direction of, and this is what you're going to have to do on a quiz or a test, the direction of the water flows into the cell. Wherever it's high, that's where the water's going to go, wherever the solute concentration is high. All right. So now let's go ahead and take a look at this again. So wherever the solute, whatever's happening outside, we're going to have specific words. Let's use these specific words. When the solute concentration is high outside, we call it hypertonic. When the solute concentration is high outside. We call it hypertonic, high outside. Hyper means high or above, right? Like when you're hyperactive, you're really active, right?
High outside.
When the inside and outside are equal, we say isotonic. That means solute concentration, I'm going to use an abbreviation here, is equal. ISO means equal. So that's what ISO means, equal. Or the same, if you will. And when the outside is low concentration, then that solution is called, what, anybody have a guess? Anybody? Some of you might know. Good. That's a good guess, really. But it's actually hypo, correct. Hypotonic, because hypo means low or under. So see, together you can figure this stuff out. So hypo means low. So that's when outside solute concentration is low.
You gonna post this video?
Yeah, as always. Is it time to go?
Yes, sir.
All right, so I'll post this video. Yeah.
That was the end of the notes, right?
Not the end. We'll finish though. All right, I'll finish with the next class if we get a chance, and I will post this. So that being said, let's take a look then at what would happen. What happens to the cell in a hypertonic solution? So what's going to happen to the cell? In which directions of water going to move in a hypertonic solution? If the solution you put the cell in is higher, what's it going to move to? The solute's higher outside than it is inside. In what direction is water going to move? It's going to move out. Why? Why is it going to move out?
Because the solute is lower.
Because water is going to move in the opposite direction the solute
Solute
would.
is higher inside.
Water, yeah. Water's going to move out. So what is that going to do? What is that going to do to the cell then?
Explode.
It's going to shrink it. It's correct. So the cell's going to shrink.
And it gonna make the wall fall? Oh, wait, no.
That's for a plant.
So it's going to shrink. Everybody okay with that? That's what's going to happen in a hypertonic solution. The cells shrink. That's what happens. Now, what happens in an isotonic solution? What do you think is going to happen in an isotonic
It's
solution?
not going to go anywhere.
It's going to stay the same. It's not going to change. No change. Same, no change. What about in a hypotonic solution? In which direction is the water going to move?
It's gonna get, but then the cell will get bigger.
So cells, the water's going to move in. Different problem set, but that's okay.
That makes sense.
Water's going to go in, but so then what's going to happen to the cell if water goes in?
Explode.
It's going to get bigger, and it could explode. It could burst. It's not really explode. It could burst, right?
It's going to explode.
But it's definitely going to get bigger and maybe kind of just, you know. There could be a rupture of the membrane, right? Could be. Doesn't have to. Are we all good with that? So those are three things that's going to happen: a hypertonic, isotonic, and because of that. So there's two kinds of. Now, what about these things that can't move very easily? What if I took and I had a cell that needed sodium? Again, I'm going to draw this without drawing the membranes, if you don't mind. I'm just going to draw kind of this. I have a membrane. I have kind of the lipid layer. I have sodium out here. It wants to get in. How am I going to get sodium in? It can't cross the membrane.
Make a channel.
Make a channel. So I can make a channel. This is one way. If I make a channel, I'm going to make a protein. There's going to be a protein in that channel. We've drawn this before, haven't we? And we have the hydrophilic or hydrophobic part here of the protein. And then we have the hydrophilic part of the protein kind of sticks out in the membrane. Everybody okay with this so far? Just like before, no big change here. And then the at this point, then we all should know that the sodium is going to go from high to low. High to low. High to low. You're going to have sodium ions coming in. Why do you have sodium ions coming in? Because it's high outside and low outside. Is this still not diffusion? This is diffusion, right?
Yeah.
High to low. No extra energy. Do you agree?
Yes.
Wait.
Don't just say yes. Do you see that it's moving from high to low, no extra energy? Yes or no?
Wouldn't the protein, to make the protein, wouldn't it get energy? Wouldn't it need energy?
Okay, so to make the protein need energy, it needs energy to move, but you don't have to add any extra energy. So you're going to use what's there that's coming in, correct? But it's not just diffusion, is it? Because there's something else going on. You're using a protein, like you say. There's a protein helping it. What's another word for help? Help, assistance. Assistance, help, what else? What is it? A receiver, kind of, no. There's another word. If I'm helping something, some people might call me a friend. Call me a facilitator. So to facilitate, so this is actually called facilitated, good guess, facilitated diffusion. So it's diffusion that gets help,
By a protein.
right? Yeah, usually a protein, correct. So it's facilitated diffusion. Diffusion is still going from high to low, but it's getting help. So we call it facilitated diffusion. Everybody okay with that? All right. So that's facilitated diffusion. Now, there's simple diffusion. So simple diffusion is when it crosses by itself. So let's look at the different kinds of facilitated diffusion. What is a concentration gradient, and what is Fick's law? Fick's law. All right. One, a concentration gradient. Do you all see that this is not dark gray here and light? It's not dark gray and light and white, correct? There's dark gray, a little lighter gray, a little lighter gray, a little lighter gray, a little lighter, then it gets white. Do you agree? Look at this, because this is important. There's no, I don't really have a way to explain constant gradient unless you're looking. So here you have, oh wait. Here's dark gray, correct? And it gets lighter and lighter all the way over here to the least dark, correct? All right, that's called a gradient. So also, and you have a high concentration, highest concentration here, correct? Becomes less concentrated, all the way out here till you have the least concentrated. We call this the concentration gradient. So when things diffuse, they go from their high to what? High to low. All right, concentration gradient. That's the direction things move without any extra energy. I am not worried about this Fick's law. It'd be nice if we get a chance, we'll cover it, we'll go back and look at it, but I don't think we're going to have time to really calculate how fast something's moving. But I think it's common sense. How fast something diffuses depends on the surface area, the difference in the concentration gradient times the surface area, times how far it has to go. And when we do the lab, we'll go back to this, we'll come back to this. But let's look at the different kinds of diffusion, of passive transport. No extra energy.
So passive
Diffusion is a type of passive transport. Passive transport means what? No extra energy. No extra energy. You don't have to add any energy. The energy of the system is enough. The kinetic energy of the system is enough. So let's take a look at it. Simple diffusion. The word is simple diffusion. It's actually a term. You need to know it. You need to know the definition. Simple diffusion is here, A, and here it is. It's defined for you. Do you see that? Every one of these is defined. A is this, B is that, C is that, D is that. Are we clear? So simple diffusion is just when things go from high to low. That's it. Notice these white larger spheres, these lipid soluble solutes, go from high to low. Do you see that? So what would that be? That would be carbon dioxide, that could be oxygen, These are dissolvable in water, but they also go right through the membranes of the cell. That makes sense, because how would you breathe if you couldn't get it past the membrane, right? If you took a deep breath, how's that getting into your blood? You have to get, it has to get past your cells. Correct? So these molecules get across the membrane through simple diffusion. They're small, they're nonpolar, they're soluble in water and in fats, and they go across the membrane. These are called simple diffusion. Osmosis is the diffusion of water crossing the membrane from waters high to waters low. Now, water can pass through the membrane even though it's polar. Is that clear? Because it's small. But it happens so slowly that your cells need help, so they do use facilitated diffusion, because they have, look, there's the facilitator. Do you see that? Do you see the facilitator here? A protein that makes a channel that allows water to flow through. Facilitate from high to low. Nothing's helping it. No energies, no extra energy. It's just going from high to low. It's using a channel to help it. So this is facilitated diffusion. If it goes by itself, it's just diffusion. Do you understand that? If it uses a protein, it's facilitated. Another facilitated diffusion example is a carrier. So here, notice the difference between a channel, like an aquaporin. Oh, by the way, it's the term is aquapore in. Aquaporin. This is a pore, like a hole in the membrane, for what?
Water.
For water, aqua. So what happens in this kind of facilitated diffusion is, in this case, sugar attaches to the protein. When it attaches, the protein changes shape. So here it's high, it lands here, and then it opens up on the other side, and in it goes. So it's still diffusion, still going from high to low, but you're using a facilitator. It's called a carrier. So one's a channel. One facilitated diffusion is a channel. The other's a carrier. Now here's another example of a channel. So facilitated diffusion through channels, where here you have inorganic ions, like maybe it's a sodium or chloride, and it's going through the channel from high to low. Again, it's facilitated, it's being helped. But it's no extra energy, so it's still diffusion. Are we all clear on this idea? Because we're moving on. All right, so let's move on.